introduction. And first, I'd like to thank Marielle, Patricia, and Sandra, Davide, and Vitriana, so all the organizers for giving me this very great opportunity. So I am very, very honored to give a talk in this very special occasion to celebrate Claudio. So today I will talk about our recent joint work with these people, Kenichi, Yukio, and Jun Koriki, Hideta Owachi, all from Keio University, and Shuji Yamamoto, who is now in Shimane University. Okay, so let me start. So today, first I want to explain what is the motivation of this study. It's a bit, I think, a bit different approach usually we do, where we focus on some specific model and find what is the interesting phenomena or what is the new observation for this model. But mine is a bit different, so we'll take some time to give motivation. And then in the second part, I will talk about our general framework to study interacting particle systems. And this part is no probability and no analysis, so it's just about some combinatoric property and algebraic property of particle systems. So I hope you can easily follow and enjoy. And I think this part is somehow a bit new for all of you. And the third part, I will tell you about cohomological and Hodge theoretical approach for non-gradient models. And I think this part will be a bit technical, but still I want to, I will try my best to try to convince what happened. Okay, so let me start. Yeah, so the motivation. So of course, all of you know here the hydrodynamic limit for interacting particle systems, and it's related limiting theorems like fluctuation, CRT, associated to the hydrodynamic limit or large deviation, also some tagged particle problem or the scaling limit of current and so on. So there are so many have been widely and actively studied for over 30 years. And of course, as Stefan already said, but there's no doubt that the textbook written by Claudio together with Kip Nist played a very important role in shaping this field. And I actually learned all things from your book, essentially, in this field. So I really thank you, Claudio. And especially for special models such as the exclusion process, a wide range of variations such as the symmetric version, a weak asymmetric version, long-range version, or degenerate version, or even KPZ time scaling limits, like we add some weak asymmetry and we derive a stochastic Burger's equation, exactly explained by Stefano in the last talk, and also some models with boundary condition. So many things are well understood, and of course there are still many questions, and this is why people are still working on the exclusion process. But yeah, so for this exclusion process, I think we understand a lot in these 30 years. But on the other hand, even for just we restrict finite range and reversible models with periodic boundary conditions, for my understanding, there's no general unified theory. And in particular, when trying to understand universality, it is unclear what class of models we should consider. So what this means, for example, if we consider about the very classical CRT for IID sequence, maybe people start from some specific distribution like Gaussian distribution, Bernoulli, or binomial, and then for each specific distribution, people find how to prove the CRT, and then later, finally, we now understand just to show CRT, the condition necessary and the sufficient condition is the variance. Variance is finite, a second moment is finite, and so in that way, if we want to understand what is necessary and the sufficient condition for hydrodynamic limit, we first need to understand what kind of classes of models we want to study. So like IID sequence, or for example. So, and I really hope to understand these interacting particle systems in such a way of the level of universality. And also, only a limited number of results exist for models with multiple conserved quantities compared to a single conservation law case. And this means there are multiple macroscopic variables. And of course, yeah, we already heard from Stefano's talk, nowadays people are more interested in the case where multiple conservation law exists. So I want to understand this unified way. And the model in mind in this talk is the examples are the following. For example, maybe this is easier. Okay, for a single conservation law, maybe you know what is the exclusion process on, and here so far I focus on what is a state space and what kind of a transition can occur. And I somehow ignore what the jump rates are. So in the exclusion process case, we have this type of state space. And of course, we can consider not only ZD, but on the discrete torus or any more general graph. But this is one example. And also, we have an example called generalized or partial exclusion processes, where each site can contain at most alpha particles. So there's a limit, but the exclusive interaction between particles are somehow relaxed. And the typical state space is like this. This is for D equal 1 case. And also the range process where there's no restriction on the number of particles on each site. And also there's a model called generalized misanthrope process. And this has the same state space like this. And actually generalized here means we allow multiple particles on the site may jump together to another site. So for example, 2 particles can jump at the same time together from one site to other sites. And actually this case includes include the discrete harmonic models or discrete KMP models recently introduced. So we can consider at least such examples in mind for single conservation law case. And multiple conservation laws case, the most typical model is multispecies or multicolor exclusion process. And now mathematically, we have exactly the same state space of this generalized exclusion or misanthrope process. But now these numbers are not the number of particles, but the color of particle or type of particle. So 1 means, say, red particle, and 2 means there's a blue particle, and so on. And there's still exclusive interaction between them. So each site can contain just 1 particle, but with different color or different species. And also multi-lane exclusion process is another maybe natural example. And here, each type of or each species of particles moves through its own designated lane. So this means the red particles have its own space of exclusion, and the blue particles has its own lane of exclusion. And so they can be at the same site if they are different colors or different species. But between the same species, there's an exclusion rule. In that case, the state space becomes like this, for example. So, and what kind of hydrodynamic limit is expected to such models? So this is just the image, but for reversible multi-species exclusion process, for example, but it actually not yet rigorously achieved in general. In general means if these particles have a different speed of diffusion, for example, such case to naturally become non-gradient problem, and the macroscopic PDEs are not somehow not nice object, so it's not easy to treat. But some special cases already understood. But for this case, at time 0, we assume that this particle system converts to some continuous profile after scaling in space, properly scaled. And then we expect at time t, this particle system evolving following some Markov process also converts to some continuous profile. And we hope to understand what is the macroscopic evolution from this time 0 to time t in this continuous level. And the expected hydrodynamic limit is a system of PDEs, partial differential equations now, for the sequence of density of each type of particles. So rho 1 represents the density of red particles, and rho 2 represents the density of green particles, and so on. And then if the system is reversible and good enough, then we expect to obtain such a diffusive equation. And here is the diffusion matrix D, which depends on the total law for all the density. And the question is essentially how to obtain this D is a problem. And of course, alpha is the number of species in this model. Okay. So now I want to explain what is the general framework to study these models in a unified way. So first, I need to introduce some new notions. And first, just the local state space S is a non-empty and finite set, and describing the possible state on a single site. So in this talk, I will focus on a finite set case, but there are some results trying to generalize this framework even for continuous S or countable S. But in this talk, I focus on the finite case. So exclusion case is just a 2-point set, or generalized exclusion case, it's just this set, alpha plus 1 point set, and this misanthrope case is also the same. And multispecies case, we can also write this way, and multilane exclusion process is given by this. And here, as I said, I do not think about jump rate, but essentially we focus on what kind of states are allowed in the dynamics. And now the point is here. So an interaction phi on S is a subset of this full product of object. But here, especially what the point is, the pair S times S and phi forms a symmetric directed graph. So if this holds, then we call phi is an interaction, or just a pair of S phi is an interaction. So what this really means, so now this phi is a set of all possible instantaneous transition between the states on adjacent sites. So in our models, usually in mind is even a long range or boundary case, or so in weak asymmetry, or even for many settings, we usually expect that all transition can happen only between two adjacent sets, and the others remain the same when the instantaneous transition of the states. So we first focus on what kind of a transition on two sites is allowed. And for example, exclusion case, just 1, 0 can become 0, 1. And of course, the opposite is possible. So because I now assume a symmetric graph, and I don't want to write 1, 0, 0, 1 and 0, 1, 1, 0, so I just introduce this notation to denote the pair of transitions of one direction and the opposite direction. So this means the exclusion case, this phi is just a 2-point set where 1, 0 and 0, 1 and 0, 1 to 1, 0. And the generalized exclusion process case, now we have allowed this type of transition. So M and K, so M particles and K particles, the site are neighboring, then one particle can jump from one to the other. So this is one edge, Mk become M minus 1 to K plus 1, and the opposite is also allowed, but only when M is bigger than or equal to 1 and the K is smaller or equal to alpha minus 1. And now generalized misanthrope process where we allow multiple particles can jump at the same time, then in this case the edge set become Mk to M minus L and K plus L. So L is now the number of particles which can jump at the same time. And so L is allowed to 1 to alpha. So now this has more edge set than this one. And the exclusion case, multi-species exclusion case, in this talk we always assume that so different type of species can exchange their position. So Mk can become Km, and just to choose one direction, I just decide K is more than M, but it's not important. So just the two states can exchange their sites. So And this way, we can understand these models as just a graph of these things. So we have graphical representation. So for exclusion case, so we have S equal 2-point set. This means S times S has 4 points. So this is the graph, and 4 points in this graph, 4 vertex in this graph, and this represents 0, 0, and 1, 0, and 0, 1, oops, and 1, 1. So now 1, 0, and 0, 1 has an edge, which is symmetric here, and there's no other edge. So this is the representation of exclusion interaction. Now consider generalized exclusion with alpha equal 2. Now S has 3 points. So S times S has 9 points. So there are 1, 2, 3, 4, 5, 6, 8, 7, 8, 9. So 9 points, 9 vertices here. And this represents 0, 0, and 1, 0, 0, 1, and 2, 0, 1, 1, 0, 2, and 2, 1, 1, 2, and 2, 2. Then the edge sets are given by this blue things. And now generalized misanthrope interaction is essentially almost the same as the generalized exclusion case, but we also add a new edge between here and here. So now 2, 0 can directly move to 0, 2. So there's a new edge. So to make clear the difference, I put a red color, but of course there's no color of edges, so all the edges are the same. But okay. And multispecies exclusion case with alpha equal 2 case, now we have again 9 points in this graph, but now this edge set is a bit different, but almost quite similar, but 1, 0 can become 0, 1, and 2, 0. Now 2, 0 means a red particle and empty site neighboring, and this can be 0, 2. And 1, 2 can be 2, 1 can be 1, 2, but there's no edge between 2, 0 and 1, 1, or 1, 1 and 0, 2. So that is a graphical explanation. And multi-lane exclusion process case, now we have 4 points in this local state space, and this means this graph has 16 points, and it's a bit complicated, but still we can write as a graph of these local interactions. So in this way, somehow we can understand this local interaction is just a graph, symmetric graph or finite graph. And now I want to introduce a key notion called conserved quantity. So for an interaction phi, the edge set on S times S, we define a conserved quantity to be a function, C, which is just a function on one side, just one side local state space, such that before the transition and after the transition, the total sum is conserved. So it's a quite natural definition, I believe, for you. For example, exclusion case, 1, 0 becomes 0, 1, but the total number of particles are conserved. So the sum is conserved. So this is, and this holds for any edge. And of course, the constant function is trivially a conserved quantity. So denote by this notation, conserved by S, the R linear space of conserved quantities modulo the space of constant functions. So we don't want to count this constant function as a macroscopic variable, so we do not count this, but we consider this space as a quotient space. And let C phi be the dimension of this linear space. So this is now a linear space, so we define this as a dimension. Then exclusion case, it's easy to show that this space of conserved quantity is just spanned by this function, the number of particles. And this is true for an generalized exclusion. So there's no other conserved quantity, and we can prove that there's just one-dimensional space. And generalized misanthrope case is also the same. So this case, the C phi is just one, so one-dimensional space. And the multispecies exclusion case, now this space is spanned by a function like, so this is a characteristic function of this site S is exactly k. So this just counts the number of each type of particles. So this means that this space is C phi, the dimension is alpha. And multilane exclusion case is also a similar thing happens, and we can prove that the dimension is alpha. And why this definition matters? So this quantity C phi, you can imagine that defined in this way is expected to be to represent the number of macroscopic variables in our original microscopic models. And if we define a conserved quantity simply as a function preserved under all possible transitions, that is just a function on this product space satisfying this, then this is just the number of connected components of the graph. So if we use this definition as a conserved quantity, then number of connected components for these models, like for example, this is 3, so 1, 2, 3 connected components, 1, 2, 3, 4, 5, and this is 1, 2, 3, 4, 5 again, and this 1, 2, 3, 4, 5, 6, and there are many. So this is certainly not the number of macroscopic variables we want to count. So this does not match the number of macroscopic variables, and adopting this definition of C phi is somehow the key of identifying the number of macroscopic variables from general microscopic interactions. And I will later also say why this definition is useful. But so there's a very simple open problem. So is there any simple way to compute C phi from the graph structure of S times S phi? So if you are given a local interaction rule, can we say how to count the number of macroscopic variables? Or is there any nice characterization of C phi in terms of the graph structure? It is still, we don't know. And not like number of connected components, we don't know how to compute this in general. Okay, now we are given this general interaction. So we can construct a configuration space that is, okay, suppose an interaction S phi is given, then the XE be a connected symmetric graph which represents the underlying graph of interacting particle systems such as a discrete torus or ZD, and then configuration space is just the product, direct product of S on all the X. So X is the vertex set of the underlying graph. So each site or each vertex we associate one local state space. So you can imagine just this is a 0, 1 to GD, so the product of 0, 1 to TD for exclusion, for example. And then for each eta in this space, and we choose one edge in the underlying graph. So this edge is a place where transition occurs. And phi is, we choose one type of local interaction which occurs. So once we choose an underlying edge and one edge in the interaction, local interaction rule, then we can always define this new configuration where if this eta or E and eta TE, so this chosen 2 points has exactly the configuration S given by here, then we change a new configuration to S from S to S prime. And of course, we keep all other sites to be the same as before. And if this original formulation does not match S at these 2 sites, and then just we keep the new configuration is the same as before. Okay. And then we have a set of all transitions here. So from eta to eta E phi, where E is the underlying edge, and the phi is from local interaction. And we do not want to include a self loop in this graph, so we assume we take all the pairs such that eta and eta E phi are really different. And then this is again an edge set. We can consider this as an edge set of this very big vertex set. so this is a symmetric directed graph, Sx and phi e, constructed from this data S phi and xe. And this is called a configuration space with a transition structure. So we call this way. So this way we can construct from any underlying edge and any local interaction. We have a big, very big graph, which is still symmetric. And for example, nearest neighbor models, we can just consider on ZD, just consider this one as a graph, underlying graph, but also if we consider short range models, short range jump models, then we can consider some different edge set. So where particles can jump, we put edge in the underlying graph. Then we have some different models. And the long range jump case, we just consider edge set is all the pairs of ZD, ZD. Then this can be understood in the same way. And also models on a more general lattice, or even some other type of graphs, and even, of course, a finite graph is okay, any graphs. And now, so the question is what condition we need to prove the hydrodynamic limit. So maybe vague and very big question, but we believe that we conjecture that the only necessary assumption on the interaction are that, okay, first the C phi must be bigger than or equal to 1, otherwise there's no conservation goal and we don't see any macroscopic equation we expect. And the only following condition is the key, so which is called irreducibly quantified. So an interaction Sy is said to be irreducibly quantified if for any finite connected graph, lambda and E phi, so finite graph, the following holds. So if two configuration eta and eta prime have exactly the same total conserved quantities, namely total sum is the same for any conserved quantity, then eta and eta prime are in the same connected components of this configuration space. And all the concrete examples I showed you are all satisfy this condition. And this condition is just equivalent to the corresponding Markov process being irreducible on any finite graph with under the constraint that the total conserved quantities are fixed. And this is not always true because we just define a conserved quantity as a very local property, and so it does not hold necessary for any interaction of phi. So when this condition holds, so S phi is first, we can check that this is irreducibly quantified if and only if the condition holds for any finite complete graph. So in the definition, we say any finite graph, but the complete graph is enough. But so unfortunately, for any n, there's an interaction such that this condition holds for all complete graph the size less than n or equal to n, but it does not hold for kn plus 1. So that is an interesting observation which we didn't expect at the beginning, but so it's a bit complicated condition. And still, this property is actually decidable, means it can be checked by a finite number of steps. So this is a recent result by one of my collaborator, Wachi, with a PhD student. So this means at least we can check this condition for given interaction by computer with finite steps, but it's not easy. And then how reach this class of models that satisfy this irreducibly quantified condition? So that is the result somehow, the classification of interactions. And okay, so I want to focus only on a separable interaction. And separable means for any 2 points in local state space, they can be distinguished by a conserved quantity. So at least there exists a conserved quantity such that the two are different. So otherwise, essentially, 2 microscopic states, local states, cannot be distinguished by a conserved quantity. So we focus on these separable models. And then by identifying interactions up to relabeling of elements. For example, just relabeling the model other than S should be thought as the same. But also we consider a bit strong, weaker equivalence between interactions. that if there exists bijections that induce isomorphism between the corresponding conserved quantity space, then we say they are the same model. And then the number of irreducibly quantified separable interactions under this classification is as follows. So if S has just 2 points, 0, 1, then there's only one model, which is the exclusion interaction, for example. And if there's 3 points, and then the single conservation law model is just, there's one single conservation law interaction, which is generalized exclusion process. And there's one interaction with the 2 conservation laws, where multispecies exclusion process. And if there are 4 points in the S, then there are 2 different class of models with a single conservation law, and 2 different interaction with 2 conservation laws, and one with 3 conservation law. And we can characterize what they are, but there is some new, at least for me, new model which was not studied before. And if there's 5, then this actually computed by computer, so it's hard to check one by one by hand, but there are some classification. Okay, so maybe because I want to say some words about non-gradients, I will not say about the new model, but some comments are, okay, in our equivalence relation, generalized exclusion and the generalized misanthrope are the same. So they are really the same in our sense. And okay, still the question is how many equivalence of class of separable interaction exist for this, and how many are irreducibly quantified. So this is still an open problem. But so this tells us a lot of new models. Actually, we have a lot of candidates to study. For example, weak asymmetric model or a long-range model with boundary models, or and they even coupled KPZ. Or so we can think about these models maybe for one by one if you want. Okay, so sorry, I will quickly say some words about non-gradient, but this part is maybe quite technical, so you can just think, relax. And okay, so now we have what is possible transitions in this unified approach, but we need, of course, the information of jump rate, and then we really know what is the model. And so the jump rate is just a function. We can consider this is just function on the edge sets of this configuration space to some positive numbers. And then we have this triplet, the interaction and underlying graph and the jump rate. Then we can construct such generator, at least formally, formal generator. Maybe not well defined for some case, but this jump rate just tells us how often eta will be changed to eta prime in this. So somehow we can consider this interacting particle system is a random walk on this big graph, and the diffusive scaling limits for this process, in particular the non-gradient method, is a homogenization theory of this random walk. So that is my main message. And but to understand the classical CRT for random walk, just one particle case, then actually, if we want to understand the theoretical point of view, these are crucial conditions. So first, the graph is connected. So it seems very trivial, but if we have 2 different connected components of the graph, then one particle on random walk may not converge to one de Brownian motion, at least to 2 different de Brownian motion. So the dimension of this kernel is very important. Kernel is this operator, so it's just the difference between 2 points. And also the dynamics invariant under the translation. So it's a kind of homogeneity is important. And so why they are key? So we ought to say some words about the random walk case, just a not configuration space case, but the random walk case on a lattice, on a crystal lattice. So just you can consider on ZD if you're. And then this case, so we have such decomposition of forms, one forms. One form is just a function on edge set. And here what they are saying is if we have some form, which is given by derivative of a function and translation invariant. Then this is decomposed into the derivative of some translation invariant function plus some finite dimensional remaining term. And this remaining term is really coming from some information of group action. So it's really algebraic object, and group action plays a role. And just for this case, Wj is just a simple xj. So this xj has a property that this itself is not translation invariant, but it's a derivative somehow. So the difference operator between points are translation invariant. So there's a gap between the derivative of translation invariant and the original function invariance, translation invariance. And this gap really give us this decomposition. And then once we introduce some edge weights, and then this edge weights introduced under some reversibility condition, then we can introduce some inner product for these forms, and maybe you can see. And then this decomposition can be, this decomposition can be generalized to the completion of this space with respect to this inner product. But actually, in this random walk setting, this completion do not do anything because this space is originally finite dimensional. But then this decomposition gives us also another decomposition, which is orthogonal decomposition. So now once we introduce some inner product in this space of forms, then there's a natural orthogonal decomposition, which might be different from topological decomposition, where we do not have any information of the inner product or edge weight. And then we have these two different bases of this cohomology. Cohomology means the difference gap between this space and this space. And then so we have two different bases of this cohomology. And if we introduce the change of basis matrix between these two bases, then actually this, the inverse of this becomes the homogeneous diffusion matrix of the random walk generated by this operator. And this is really the story behind the correct thing. So in this way, we can understand the diffusion matrix as a very geometric and hot theoretical way. So because I have 2 minutes or 10 minutes. 10 minutes. Okay. I thought almost. Okay. So now, okay, I will go a bit slow. So back to the configuration space. So what is our setting? What is the topological decomposition and the orthogonal decomposition? And what is a period matrix? So maybe then I have time to explain what is a period matrix. So period matrix is used in algebraic geometry or number theory in a very different field from ours. But so the idea is essentially if we have two different type of bases of some cohomology, and then we see what is the change of basis matrix. And this is a period called period matrix, and especially one basis coming from some topological data, topological information of geometric object, and the other basis is coming from some more geometric derivative. So some metric type of information, or some more complicated structure, like a complex structure, or not just topological, but more higher structure. So if we have two bases related to different structure of the same object, then we consider this period matrix. Okay, so now what is this for our Sx phi Pe? And then the difficulty is for our configuration space, especially if X is infinite, like ZD, then this class typically has infinite connected components, and also not locally finite, so it's a very wild graph. And in particular, dimension of this space is infinite. So, and then the story of what we did cannot work because in the last random walk case, the point was actually this H0 space, the kernel of nabla is a constant function. So there's only one component. But we introduced a new class of functions. It's not really a function, but which we call the uniform functions, instead of just all functions on this vertex set, but we somehow choose a class of functions. and still this operator is well defined. And then if we change this domain of this operator, then we can show that this is a finite dimensional space having good information of macroscopic property of the model. So uniform functions, I don't give a precise definition because it's a bit complicated, but there are several ways to define, and they are same up to isomorphism. And formally, they are represented by a formal sum of this type of thing, where lambda is the finite subset of x, and if lambda is a local function, depends only on each x from x lambda. And the point is there exists some r such that the diameter of lambda, diameter is bigger than r, then if lambda is 0. So the typical example is like this. This is of course a formal sum, but in a sense, uniform function sense, this is really a well-defined object, and it's a kind of total sum of this conserved quantity, for example. Or in case x equals zd, this function, sorry, maybe I should not use this notation, forget about this, but this thing, so each side x, xj times x is also a uniform function, because this is just the diameter of lambda is 1 or maybe 0. So this is a uniform function. And also for on ZD or crystal lattice or hexagonal lattice, this thing for local function, and we translate all over the lattice and then sum up. This is also local function. So these important objects in non-gradient method are all uniform functions. And our main theorem is the following. So an interaction phi is said to be exchangeable if any two ST and TS are in the same connected component of this the graph. So it's a really mild condition, even milder than irreducibly quantified condition. And just under this condition, and XE is an infinite connected graph, then this kernel in this uniform functions is really given by this sum. And this dimension, the space of dimension, is the same as the space of conserved quantity. So in this way, the definition of conserved quantity is really key to understand this topological observation. And the key is this thing, for example, this is formally a conserved quantity for exclusion process, for example. But once we expand in this way, this is not a uniform function. So we really do not count such a conserved quantity or the element of kernel. So this is not in element of this kernel in our restricted functions. But if we use the original one, somehow we count this. Okay, then using this, the topological decomposition can be automatically obtained in the exactly same way. And now the gap between the translation invariant one forms or the derivative of some function which is translation invariant and the derivative of already translation invariant functions. So this gap is a cohomology, and this gap is really computed just by simple way and coming from group operation. So group operation, group action give us this gap between them. And this the basis is just given by this thing, which we usually know, what we often know if you have ever worked on a non-gradient thing, then this thing. And this space is given by this one. So we have already the decomposition of this without any information of the jump rate or any information of measures or reversibility, or we don't need anything, but we already have this decomposition. And then once we introduce the jump rate and the reversible measures, so we assume now introduce the jump rate, which is translation invariant, and also we assume this thing is always a local function. And we also so far suppose there exists a product measure, where nu is a proof support probability measure on S, which is reversible for this jump rate. And we actually, this class is quite rich. We can construct many models satisfying this. And and this reversibility, under reversibility condition, first we can prove that for any conserved quantity, this measure, tilted measure or Gibbs measure, given by this, depends on the conserved quantity, is also reversible with respect to the same jump rate. And there's no other homogeneous product reversible measure. So maybe we can also prove there's no other reversible measure, but still it's an ongoing work, and we are not, we do not get enough proof. But and once we fix the basis of this, then we have a parameter of rho, parameter of the measures. And then we can go exactly in the same way as the random walk case. So we introduce some inner product between forms, and like this. Okay, I will skip. And then we have a natural completion of this space with respect to this inner product. And there's natural orthogonality composition. This is automatic that they are Hilbert space, and this is a closed form, closed space. So we have a completion. And we take basis of these harmonic forms, which is the orthogonal part, by taking this some special way. And then we have a nice variational formula, and also, so we can define D and sigma as a period matrix. Okay, so it's a kind of, so now finally it's a unified conjecture for hydrodynamic limit and the equilibrium fluctuation. So with this way, we can define from very general framework S phi and Xe and R, and assuming that there's a reversible product measure, then we should have these equations. And D and sigma are all well-defined object now. Okay, so but the last remaining task, maybe you want to know. So remaining task is essentially uniqueness of the weak solution and equivalence of ensemble. Actually, this is not totally clear for in general setting. And of course, we need a sharp spectral gap estimate so far to use a non-gradient method. But at least under this condition, once we have a sharp spectral gap estimate, we already proved that the key property of the non-gradient method actually hold. So there's only a remaining part to do. Okay, thank you very much. I stop here.
Okay, thank you very much, Makiko. Is there any question? Yes.
So, in your theorem about decidability, do you have a bound on how far you have to go in the complete graphs? You have to look on the complete graph if your interaction is, let's say, order
irreducible or not.
Finite order, given finite order 2, 3, 4.
Okay, first, this decidability result is not my result. So one of the students watches the result, and he used really kind of algebraic technology, which the problem is reduced to some decidability of monoid of something and so on, and I could not follow the details, so sorry, I cannot answer your question actually. Maybe there's some bound, but I don't know, sorry.
And what is the obstruction for the spectral gap inequality?
Obstruction, yeah, so this is really my interest that I believe in this framework where S is a finite set, and we assume this irreducibly quantified condition, maybe we can prove for any case spectral gap sharp estimate, spectral gap estimate holds. But so maybe there's no obstruction, but just we need the proof, and maybe it's not a simple thing.
Other questions? Yes.
So, do you know if there exists any relation between the period matrix and the existence of a duality function when the process is self-dual?
Duality function. I don't know.
From what I understood, your period matrix can be understood like a change of basis, right?
Okay, yes.
And duality more or less does like that. There's something similar.
Okay, but the duality, it's about somehow we can connect the two different essential processes or two different states, but with some way. But the period matrix is somehow about one object or one process. So we can consider the topological property of this process. For example, we forget about jump rate and just we focus on what kind of transition is allowed. And only on this level, we have some nice topological decomposition or some basis, topological basis of cohomology. And if we add the information of jump rates, then we have more information of this process. And then we have another decomposition called orthogonal decomposition, or the basis, harmonic basis, which coming from the information of this jump rate or inner product. And then to connect these two different bases is a period matrix. So maybe the duality thing is a bit different topic, I think.
Okay, thank you. Last questions? No? Okay, so let's thank Makiko again. Thank you.